Hi, welcome back. In today's video, we're going to talk about how do you find the hole in a rational function. Now, we're going to talk about what a hole is, when does it happen, why do they happen. But literally think about a hole, right? We're going to be graphing a function, and then somewhere along the way, there will be a hole in it, okay? I'll tell you why it happens, when does it happen, and how you can make sense of holes in rational functions. So let's do a few examples. As in my previous video, my focus primarily for this video will be holes. Even though there's vertical asymptotes, horizontal asymptotes, x and y intercepts, there's a lot of attributes to a rational function. I'm not going to focus specifically on how to find the other ones. If you want to, you can watch those specific videos for those topics. This one will be primarily focused on how do you find the hole of a function. So let's get to it. Here we have a function. And the first thing that I want to do when I have a rational function is I want to simplify the function, right? I want to work with the simplest form. So I'm going to start by factoring the numerator, the denominator. Notice how they both are divisible by 2. So if I take out a2, right, dividing the top by 2, I am left with x squared minus 4. And the bottom, they're also all divisible by 2. When I do that, I am going to be left with x squared plus 5x plus 6. Now that I factored out a common factor, I can factor these as well. Factor the numerator, factor the denominator. Now the numerator, x squared minus 4, is going to be x plus 2, x minus 2. Right? And then the denominator, 2 times, for the denominator, I'm going to do x plus 3, x plus 2. Now, if you want to do the 3 columns, you can do that. X squared, you can add a 0 in the middle, subtract 4, right? You can go through that process, x times x, 2 times negative 2. For the other one, you'll have x squared plus 5x plus 6. You can also do the 3 columns. That's 2 times 3, right? That's how I got these right here in the bottom. Now, once I've factored everything out, notice how I'm able to cancel things. This x plus 2 also gets canceled. And the function now simplifies to f of x equals x minus 2 over x plus 3. These two functions are mostly the same, except that one of them is a simplified version of the other, right? Now, I'm going to be working primarily with this function for me to graph it, for me to deal with it, so that I can see how it behaves. If we look at our previous video, vertical asymptotes occur when you divide by 0. So if I set the denominator equal to 0, I can move this over. I have a vertical asymptote at negative 3, which means I'm going to have an imaginary vertical line right here. Right? So this will help me define my table. When I create a table with points, I always focus on the vertical asymptote, which is negative 3. This is undefined. And I look at points around it. I'm going to plot points negative 4, negative 5, negative 6. Points over here to see if it's pointing up or if it's pointing down. The same thing over here, negative 2, negative 1, 0. Where is it pointing? Right? We know that it's going to approach the asymptote, but where is it pointing and what direction is it coming from? So you can always plug these points in. Right? So when I plug points in, you're able to plug it into the new function that's simplified or the original. Right? You can plug them into both and you'll get the same solution. Like, for example, if I plug in 0, I'm going to plug 0 in here, one of these values, 0 into this function. I got 0 minus 2 divided by 0 plus 3. This comes down to negative 2/3, or negative 0.6667, right? That point exists here. Now, if I plug it up here, plug 0, since it's not simplified, I'm going to have to do a little bit more work. but it'll still work out, right? I got 2 times 0 squared minus 8 divided by 2 times 0 squared plus 10 times 0 plus 12. I just have to simplify some more, right? Do PEMDAS a little bit more. 0 squared is 0. 0 times 2 is 0, which gives me just negative 8. 0 squared is 0 times 2 is 0. This is 0 plus 10 times 0 is 0 plus 12. When I simplify that, I'm going to get negative, divide everything by 4, negative 2/3, which is also negative 0.667. So notice how for both of them, I get negative 0.667. So it doesn't matter if I plug in the value into this one or into this one, they're the same function. And I should get the same solution. Yeah. So as I plug in all of these points, the graph will end up looking something like this. When I plug negative 1, plug negative 1 in here, negative 1 minus 2 divided by negative 1 plus 3. This gives me negative 3 over 2, or negative 1.5. I can plot that here, negative 1.5. So I can already tell that the function is pointing downward, right? It's going in this direction. As I get closer to the line, the points are dropping. Let's plug in negative 2. When I plug negative 2 in here, this is what happens. Negative 4 divided by 1 gives me negative 4, which is down here, right? And as you can see, I mean, the function is literally doing what we said it was going to do. It was going to point all the way down, which means on the other side, I'm going to have points that are going in the other direction. They're going to be going upward. Something like this. It'll be going close to the line, but not really touching it. Now, I want to show you something that happens here at negative 2, though. When I plug negative 2, this is what I got, negative 4. When I plugged it into this function, we got negative 4. When I plug negative 2 into the original function, what should I expect to get? The same solution. But check this out. Plugging negative 2 into this equation gives me minus 8 divided by 2 times negative 2 plus 10 times negative 2 plus 12. This is going to give me negative 2 times negative 2 is 4. 4 times 2 is 8. 8 minus 8 is what I get on top, which results in 0. And then in the bottom, right, negative 2 times negative 2 is 4. 4 times 2 is 8. This gives me negative 20 plus 12. And this also gives me 0. Now, we can't divide by 0. This is undefined. So when I plug negative 2 into this problem, I got negative 4. When I plug negative 2 up here, I get undefined, because I can't divide by 0. I'm supposed to get the same solution, but I don't. They contradict each other. So what's going to happen is at negative 2, we're actually going to get a hole, because there's a contradiction between the original problem and the new problem. There's a hole in this part of the graph. Yeah? How do I know that's going to happen? Well, when I simplified the problem, this function turned into this function. What happened here? Well, from here to here, after factoring, notice how we canceled this value out of the equation. We removed it from the problem. This, anything that we remove, will create a hole, right? We're literally removing a value, a particular point on the equation that does not exist anymore. This is the same thing as this without the x plus 2's. So what I'm going to do is I'm going to take the thing I removed and I set it equal to 0 and I solve for x. Notice how at negative 2, I have a hole. Here's what we want to think of this as, right? I am in the process of simplifying the function. I am removing a factor from the equation. And when you remove it, you're going to create a hole in that part of the graph. This is also another reason why holes are known as removable discontinuities. The graph is continuous. It's a straight line that doesn't stop. Everything exists. But now there's a part that you're removing, making it discontinuous. Yeah? Here's the Desmos version of it so that you can see what this graph looks like. Right? I know there's a lot here, but this is the part that we're talking about today, the hole. Now, when you go to Desmos and you graph it, this is what you end up working with. You have the same graph, right? The asymptote is at -3, as we did earlier. It's not going to touch -3. This is our graph. But notice how there's no holes here. We said there was going to be a hole at -2. So if I zoom in here a little bit, if I go all the way to x is -2, right? Here's -2. When I go to this point, and I get really close, notice how on the graph, even though it doesn't show it, at -2, that point is undefined. Right? We're not able to see it. We'd have to zoom in a lot to see that hole. But at -2, notice how there is no value. It's non-existent. It is undefined. Just as we predicted earlier. Right? So you won't be able to see it at first glance. But when you factor the problem out and you eliminate a part of the variable from the original equation, the thing you're eliminating, the thing you're removing, is going to create a hole at that location. That's the essence of today, right? Holes, why do they happen? I'm going to show you some more graphs so that you can see how this occurs. But it all comes down to factoring. How comfortable do you feel factoring it and see if there's something that eliminates from the equation? So, let's do another example. Let's factor this top portion, 2x squared minus 5x minus 3. Find the factors, 2x times x, right? I'm going to do either 1 times 3 or 3 times 1. I'm going to do 1 times 3, because when I cross multiply, this gives me 6x, this gives me 1x. And to get a -5, I have to do 1 minus 6, which means this came from a -3. So my factors are 2x and positive 1, and x -3. Now in the denominator, if I want, I can add a 0 in the back to do my 3 columns, right? Or I realize that they both have an x in common, so to factor out the x. If I divide this by x and this by x, what's left over? Right? X squared divided by x, you have 1x left over, and then if you divide by x, you get -3 left over. Notice how our x minus 3's are going to cancel. So my simplified function is 2x plus 1 divided by x. These two are identical in all values except where? Except this thing I removed. That's my hole. Right? Where will the hole exist in the graph? The part that I removed, set that part equal to 0. So that I can isolate the variable by itself. And I can identify that the hole will now happen at 3. This is the hole. Now this function is still graphable, right? I can still find the vertical asymptotes. I can still do all of those things, right? And if we remember back to our previous video, vertical asymptotes occur when you try to divide by 0. So you set the denominator equal to 0, and you solve for x, meaning there's a vertical asymptote at 0. There's going to be an imaginary line at 0. At x equals 0, there's an imaginary line. And there's going to be a hole at x equals 3. Somewhere over here, there's going to be a hole. So what I would do is I would plot my points. Go to the asymptote, 0. You know it doesn't exist here. And then plot points around 0. Plot negative values. Plot positive values. Right? You can plot all those values. Now I know because there's a hole at 0, this will also be undefined. This is where the hole exists. And then all the other points will help me, whether it's pointing up, is it pointing down, it'll help me see that better, right? That's the whole point of plotting in values in here, is that when I plug it into my new equation, I'm able to graph a few points, and I can see, is this going this way? Is it going this way? What direction is it going? For time purposes, I'll show you my graph on Desmos. Here's my graph. Yeah, see how there's an asymptote at 0? It doesn't touch 0, top and bottom. Now here, remember that we have an asymptote at 0 and a hole at 3. At 3, we don't see the hole, but I know that when I click closer, there it goes. At 3, that point is undefined. That point is non-existent, right? We would have to draw a circle in there to make it more noticeable, because you can't really see it the way that it is right now, right? But I know that there's a hole at 3, because at 3, that's the part of the function that we removed. At x minus 3, when we solved it, we removed that part of the equation. So the function will look like this, right? Like this, and there's a hole at 3. So asymptotes and holes are very similar in the sense that they are both undefined. These are both x values that are undefined in the graph. And they're either a boundary, like a straight line that the function is going to try to approach and get really close to, or it's a hole where things can exist around it. It's not really a boundary, it's just more like non-existent right there. There's an empty space where there's no x values that are possible. Yeah. So if you can factor the function and you can simplify it, whatever part gets canceled, that's how you find the hole. Set it equal to 0. Boom, there's my hole. All right, last example. I'm going to keep graphing things on Desmos to save time and show you the graphs. They're also better looking, you know. So let's see. Factor this problem. On the numerator, when I factor x squared minus 1, I'm going to get, let's see, x plus 1, x minus 1, right? They're perfect squares. You can also add the 0x in the middle, as I've mentioned this before, right? 1 times negative 1. You can always do that. For the denominator, it's a cubic function, or a cubic polynomial, which means the cubic will have 3 factors. Notice how they all have an x in common. So let's divide everything by x. If we take out the x, we're going to be left with x squared, negative 4x, and minus 5. Right? We took out an x from each one of these when we factored it. And that's how you're able to like cancel one of these x's and cancel one of those x's to get the x squared. Now that I've taken out this as x and x squared, I can factor this as well. I can factor x squared minus 4x minus 5. Right? I'm able to treat that as its own quadratic and then do 5 times 1. So the factors here, I'm going to have to make this a negative 5 in order for me to get a negative 4 in the middle. So let's rewrite this function. I got x plus 1, x minus 1. In the denominator, I have x times x minus 5, x positive 1. Notice how this part gets eliminated. There's the hole, right? Whatever I remove becomes the hole. X plus 1 equals 0. That's the piece that is going to create the hole. The rest of the function gets simplified to this. X minus 1 on top and x times x minus 5. Yeah. There's a hole somewhere here at negative 1. And then I'm going to have 2 asymptotes. Right? Asymptotes occur when the denominator is equal to 0. So I'm going to set that equal to 0 and set that equal to 0. That turns into positive 5. I have two vertical asymptotes. At 0, dotted line. At 5, I have another one. And then there's a hole here at -1 somewhere. So let's check out that graph, right? What would you do? You would create a table if you want to graph this whole thing. We know that 0 is undefined. We know that 5 is undefined. And we know there's a hole at -1. And then I can plug in points all around it. Plug in a few points here. 1, 2, 3, 4. Plug something in there. Plug 6, 7, 8. 6, 7, 8. 1, 2, 3, 4. And then -2, -3, right? Plug in a few points in every region. One in the left, one in the middle, one on the right. And that might take a little while, but if you're using this function, it'll be faster than plugging it into that. Here's what the graph looks like. So I'm going to move this over, right? Notice how I have an asymptote at 0 and at 5. I have 2 points that weren't going to exist, just like my function, right? My graph had it at 0 and at 5. Now, where was the hole? We said the hole was going to exist at -1. So when I go to -1, I can go to the exact point, right there, and I can see that -1 is undefined. -1 does not exist as well. That hole will be identified whenever we solve the problem and we simplify it, right? So there's 3 parts that the graph will not exist. At -1, at 0, and at 5. And the -1 is the one that's the least visible. That's the one that we'd have to do it by hand, right? By identifying the part that gets removed. There's the hole. Alright guys, I hope this has helped. Please let me know if you have any questions. Don't forget to like and subscribe, and as always, we'll calculate.